So three-dimensional shapes. Now what are these often called? I suppose these are often called solids, aren't they? A solid. So it's a thing you can pick up in your hand, basically. Okay, what are the ones that I think are absolutely fundamental? Rectangular solids, first of all. So the three-dimensional version of a rectangle, basically, is the first that we must 100% understand. So what does a three-dimensional rectangle look like? Well, it's basically a rectangle in 2 dimensions projected into 3 dimensions. So it's going to look something like this. Hopefully very familiar to us. Okay, and all the internal angles here are right angles. Every face, if you want, is a rectangle. Okay, so let's label everything as before. So we'll have A here, let's do B here, and then projected into the next dimension we'll have kind of length C there. So these 3 numbers. So this is called a rectangular solid, if you want. There are other names for it. Some people call it a cuboid, a parallelepiped, all sorts of weird stuff, but I think rectangular solid is the simplest. A rectangular solid. And again, there's a special case of this, which we should all be familiar with. A equals B equals C. That gives a cube. That's a word for that special case. That's where all faces are squares. Okay. Now, this is a special case of a more general one that I want to describe, which doesn't really have a specific name, but is a kind of a very important basic shape, or basic kind of three-dimensional type object. If I take, let's say, some sort of shape in 2 dimensions. So sorry, it's a bit of a mess. Take a shape in 2 dimensions, and let's say project it into 3 dimensions at right angles. So that sounds very fancy, but let me just show you what I mean. So let's duplicate this. Project it down like this. So we've got to use our imagination a little bit here. Like this. So what does this shape look like? Well, maybe it makes it easier to visualize this if we think about the following. So imagine that you can't see the back line here. That makes it a bit more obvious what I'm thinking here. So we've got a 2-dimensional shape, and we're basically like projecting into 3 dimensions at right angles. Okay, so let's take the shape at the top and let's call it shape S. So that's kind of a 2-dimensional shape, but I'm thinking about it kind of projected into 3 dimensions. So this is an example above, right? Because of the fact the shape S would be the rectangle on top, and I'm projecting it down at right angles to give a 3-dimensional solid. Okay, now this is a bit of a weird shape, but there are various things about it that there are very special cases which are really important. We've already seen the rectangular solid. Another example would be, let's say, well, a cylinder is a good example, where the shape on top is a circle. So e.g. examples. Cylinder, so shape on top is a circle. Whoa. Yeah. So it's this basic shape. It's nice to be able to do this pretty neatly. So that's called a cylinder. Very important example. We could do it with a bunch of other kind of geometric figures in 2 dimensions. I mean, you could do it with a triangle, quadrilateral, any polygon really. So another kind of standard shape would be something like maybe like this. If I can get it to work. If I can get it to work. There we go. So you could take this guy and you could project it to 3 dimensions like this, and then rather nicely draw lines between everything. So a shape like that, kind of a prism type shape if you want. So these are in the back so you can't see them. Nice. So there we go, that's often called a prism. Alright, so that's an interesting shape. I mean, it's very general, right, for a general shape, S, but it's an important one to understand. Another example, which looks a bit like a cylinder, is a similar kind of thing, but instead of just projecting all the way down to the same object, you kind of project down to a point. So rather than do some sort of general construction here, let's do just a special case because it's not necessary to understand in huge detail. So let's take a circle. Let's take a circle. And let's draw up to a point right in the dead center. Hopefully that's pretty reasonable. It's not too bad, is it? Okay. So this is a solid shape. It's like a cone, right? So again, this is in the back. That's another interesting shape. This is called a cone. And finally, in this kind of same direction, I mean, this circular, an absolutely fundamental 3-dimensional shape or solid is a sphere. It's another one which is worth kind of pointing out. So let's attempt to draw a sphere. Not the easiest thing in the world to draw, but we'll do our best. Maybe it'll work, maybe it won't. There we go, that's a sphere. Let me kind of really hammer home why this is a sphere. Let me imagine these lines as being in the background. So this is basically a sphere with kind of 2 great circles around it. Okay, so it's a ball, something hopefully we're all familiar with. So let's take a look at these shapes. The first one I've already kind of quantified things with these lengths A, B, and C, but I should do the same thing for the next ones as well. So this shape S1, right, this kind of quite general construction, if we drop a straight line down, at right angles, which is how this is constructed, that straight line is going to be the same for any point. It's going to have a length, let's label this length h. So that's a nice way to quantify this. Now similarly for the cone, that has a height, so let's maybe drop down a straight line to here, and it's a circle, so it's also got a radius. So let's label these two things as h and r, kind of quantifies them, or at least it pins them down completely. And finally, the sphere, of course, has a radius. The distance from the very center to the edges, which is the same for all points. So yes, I should label this as sphere. All right, so let's really get into this. For two-dimensional shapes, the quantifications were perimeter, which is kind of a one-dimensional thing, and area, which was a genuinely two-dimensional thing. For three-dimensional shapes, of course you have volume, which is the equivalent in 3 dimensions of area, and it's how much space it takes up. But you've also got a two-dimensional numerical quantification, which is the area of the surface, assuming it's a closed solid. So all of these shapes fall into that category. So the numerical quantification here would be the two things, surface area and volume. So surface area and volume. Alright, so let's go through each of these examples, determining as a formula what the surface area is and what the the volumes are. Now, first one, rectangular solid. If you take something like a rectangular solid, or really any of these shapes, and basically you cut along the edges, you imagine this is something, you've got a pair of scissors, you can cut it, then you can lay the whole thing out and lay it flat, and that gives you a genuine kind of two-dimensional shape, and it's called the net of the solid. And if you do that, that two-dimensional shape has an area, that's what we call the surface area. And if you look at a rectangular solid, it's fairly obvious-ish what the surface area, or what the net's going to look like. It would be 6 rectangles, because there are 6 faces. All right, that guy, that guy, that guy, one on the bottom, one on the side, and one at the back. So if you lay it flat, you're going to get the 6 faces. The surface area is going to be the sum of all of those individual areas. So that's 6 things, and if we go through them all, we end up with the following. So the surface area what's it going to be? So surface area well, let's just do one of them, right? So first of all, if I was to take this face here, that has area A times B, but there's another one of it on the back, or at least an identical copy moved along. So at the back, same story, right? That would be a face with area A times B. So there are 2 faces with exactly the same area A times B, so that would contribute 2AB to the surface area. And if you go around each of the faces, you get the same thing. Plus 2BC plus 2AC. Now that's not a formula you should memorize really. You should understand where it's coming from. It's coming from the fact you've got these 6 faces and you're adding up the individual areas. Now, volume is, again, much like the volume of a rectangle, essentially defined, or the area of a rectangle is essentially defined to be the product of the 3 numbers A, B, and C. That's how we define volume for a rectangle. Makes sense because the bigger A, B, or C are, the larger the volume should be. Okay, now this guy, this funny shape, this shape in 2 dimensions projected into 3 dimensions at right angles, we can actually give formulas if you want for the surface area and the volume, but we need to be a bit careful. So first of all, what about the surface area? So the surface area is, well, very interesting. It's the same story as before. We essentially need to take this cut it open and lay it flat and see what area we have. Now, two things are pretty obvious. The first is you're going to get a piece which is the shape S, and you're also going to get another piece, the shape S. So certainly you're going to get 2 times the area of S, all right, whatever that might be. But then what? Well, the edge needs to be counted. So the edge is all this stuff. But if you think about it, if you were to kind of undo this and just attach these shapes at a single point, you could take the edge, unfurl it, and lay it completely flat, and it would be a rectangle. Now, what would the rectangle be? It would be a rectangle of height h there. And what would the length of it be? Well, it would be the length around the outside, but that's the perimeter of S. And what is the area of a rectangle? Well, it's the base times the height. So it would be plus here, so this is the area around the edge, h multiplied by the perimeter of S. So I'll write it like this. So again, it really depends on S, what these are, but it's incredibly important that you understand that basic logic. So this is, again, essentially from the fact we're taking this, cutting it up and laying it completely flat. You get 2 of these, that's where this is coming from, and then the edges, if you want, the outside, can be turned into a rectangle with height h and length or width, the perimeter of S. So again, you could do that in this case, or this case, get very specific formula. What about the volume? Well, this again is not completely obvious, but it kind of makes sense when you think about it. The volume is the height, it turns out, multiplied by the area of S on top. And if you want a kind of a sanity check on that, just look at this example here. The area on top is A times C, and the height is B, so it should be B times A times C. Well, that's just ABC, so it does make sense. Okay, very important example, and it's important, certainly the cylinder is very important, and things like this are important. So you should really, I've given you this kind of very general description of it just because it turns up in various ways, and it's important you understand that it can be, well, how to kind of think about its volume and its net area. Okay, or surface area, sorry. Okay, the cone, a bit more difficult. This one's much more difficult to kind of wrap your head around. I'm essentially going to cheat and just give you a formula and let you think hard about why it might be true. So the surface area of this one is not so easy, but part of it's not so bad. So surface area here. So imagine I was to take the cone and cut it up. So what I would do would be I would maybe cut it down that line there, cut it around the edge, and then kind of unfurl it. So part of it would certainly be the circle on the bottom. Circle is area pi r squared. So that would be okay. But then what would you be left with? Well, you'd be left with kind of the, sorry, you'd be left with the edge. And the edge is a pretty hard thing to wrap your head around. But if you unfurl it, what you would notice is it's actually part of a circle, right? It's part of a circle. And if you were to work out what proportion of a whole circle it is, you might be able to work out its area. And the first thing you need to know is, well, you need to know the radius of this circle because of the fact you need to know the radius to work out the area of a circle. And the radius actually turns out to be that length there. And that length there, if you think about it, you can calculate using Pythagoras. So there's a really nice calculation that I won't go through here, but there's a nice calculation which says that the area turns out, the area of this edge turns out to be equal to pi times r times this length here, which is the square root, let me just write this more neatly, square root r squared plus h squared. So really, as I said, this is a calculation coming from a proportion of an area of a circle, and to know the area of the circle you need to know its radius, and this is the radius, and you get that from Pythagoras. So this is coming from Pythagoras. All right, that's the kind of formula. It's one of the ones you really need to memorize almost. Very often if you were dealing with a problem that would be given to you directly, just because it's a bit of a weird formula, it's not so easy to know. Another one again that I don't think is terribly easy to remember is it turns out, this is rather strange, that the volume is not something you could guess. unless you have some sort of superhuman insight. But the volume turns out to be equal to 1/3 times pi r squared h. And you may think, well, where's that coming from? If you took out the third, if you just looked at pi r squared h, pi r squared is the area of the circle on the bottom, and h is the height. So pi r squared h is actually the volume, if you want, of the cylinder. So something that's kind of cool, I think, is the volume of the cone, which could fit inside the cylinder, is exactly 1/3 of the volume of the cylinder, which I don't think is at all obvious, but it's kind of a nice fact. Okay, finally, the sphere. The sphere these are ones you just need to know. Again, generally speaking, they'd be given to you if you were doing a test or something like that. They are nice to kind of know cold, but you can't deduce them in a simple way, unless you're Archimedes, probably. So, surface area. It's kind of a cool formula. The surface area of a sphere is equal to 4 pi r squared. I like that one because it says that if you take 4 circles of radius r, then you can use those. You'd have to cut them up, obviously, but you can use them to cover perfectly the surface of a sphere. It's kind of beautiful. The volume, unsurprisingly, involves an r cubed, and it turns out to be equal to 4 divided by 3 pi r cubed. Again, probably due to Archimedes originally. All right. So that's more difficult than two-dimensional shapes, but I think it's important to kind of have gone through them at least once, make sure you're familiar with them. They turn up in calculus, really in problems where you're thinking about optimizing certain quantities. So yeah, I think maybe we should do an example of how these might turn up in, for example, a first calculus class. So let's do one which is two-dimensional, and I want to do one which kind of highlights what you will potentially see in your classes. So here's an example. Okay, so let's consider the following rectangle. The rectangle, okay, so let's just have it exactly as before. Let's have a rectangle, maybe. And let's label the lengths A and B. And let's call the rectangle R. Okay, R for rectangle. Okay, now here's a kind of a classic problem. So let's find an expression. So a formula, if you want, find an expression just in terms of A. Just in terms of A, for the area of R. For the area of R, assuming something. Assuming, let's say that the perimeter is 100. Perimeter of R is equal to 100. Now, without that assumption at the end, this would be a ridiculous question because the area is A times B. They're completely independent of each other in general because of the fact, I mean, A can be anything, non-zero, B can be anything, non-zero. Oh, I suppose it could be 0, but a very boring rectangle. So, the fact that the perimeter is 100, if you want, is a constraint on this rectangle. For example, if we said, could the rectangle have dimensions, I don't know, let's say 10 by 20? Yes or no? Well, if the rectangle was dimensions 10 here by 20, that would mean the perimeter is 60, right? So no, that's not possible. So what that means basically is there's a relationship between A and B, right? You can't just have a free-for-all of A and B. They are somehow bound together by this constraint, if you want. So let's just think about how I might approach this. First of all, in general, with no constraint, the area of the rectangle is of course just A times B. And you can't write that purely in terms of A in general, because B could be anything, right? We can't replace B with anything in A because they're completely independent. So, as I said, this is a general formula with more than one variable in it, more than one unknown. With multiple variables. So, what do I need to do here? Well, really what I need to do is take that B. So I've already got an A in my expression, don't I? That's there. It's the B is the problem. So what I need to do is to replace B with an expression involving just A. So we need to replace A, sorry, wrong way around, B with some expression in A. Now, in general, I can't do that, like I said, because there's no relationship between A and B. They can be anything at all. But the perimeter is given to us, which is very restrictive. So the perimeter of R is equal to 100. Now, what do I know? The perimeter of R is 2A plus 2B. This is where our knowledge of algebra is going to come in. That has to be equal to 100. So that's an equation now. Right, and this is, if you want, a constraint that's been given by the problem. It's externally given to us, the statement that the perimeter is equal to 100. So this is a constraint given by the problem. Right, remember what I need to do? I need to kind of eliminate this B. I can use this to do it, because I can apply the laws of algebra now to, if you want, solve this in B. So get B on one side and then an expression in A on the other. So let's do it. So this would now imply, well, let's do 2B is equal to 100 minus 2A, standard algebra. I want to get B on its own. Let's divide both sides by 2, or multiply both sides by a half. You would get B is equal to half of the other side is 50 minus A. Awesome. So what does this mean? In fact, let me just not skip a step there. This is equal to a half 100 minus, let me just get further right. Never like to jump algebra. Minus 2A, that's equal to that. So what does this tell us? Finally, I can come back and substitute that data into my area formula. It's equal to AB, but now because of the constraint in the problem, this is equal to A multiplied by 50 minus A. Done. So the thing about this is the following. The constraint has somehow eliminated one of my unknowns, if you want, and it's reduced the number of unknowns in my general formula from 2 to 1. And as we're going to see when we start to kind of study functions, expressions in a single unknown are very important, right? And they are going to be examples of things called functions, which is what we're going to look at soon. So this is kind of simplified, if you want. Now a single variable. Now a single variable, just A. So it's kind of simplified, so it's easy for us to get our hands on. Okay, so this is a very important example, because when you go on to do optimization in calculus, this process of taking kind of a general formula with multiple variables and reducing it to less variables using some sort of constraint happens over and over again. It's really crucial that you're able to do it. So yeah, so this is kind of an example of how our knowledge, if you want, of things like areas, perimeters, and that can be used in kind of a problem of this nature. So these formulas are important because this is what we need to use in order to kind of write down the area, write down the perimeter. but then there's algebra involved to eliminate the variables. So yeah, so that's kind of the basic knowledge I think you absolutely need to know when going into a calculus course related to kind of lengths, perimeters, areas, volumes of shapes.